This video is sponsored by PCBWay. Hello there and welcome back to another video. If you've spent much time in the Homelab community, or even just the computing community in general, you're probably familiar with the concept of a UPS, or uninterruptible power supply. UPSs are absolutely awesome, because they allow you to connect gear through them, such as computers, monitors, and networking devices, and when the power goes out, the UPS can kick in with its batteries to keep whatever was connected to it online, ideally without so much as a hitch. Now, one very popular thing to connect to a UPS for power backup during a blackout is your home networking gear. Think of stuff like your modem, router, switches, and Wi-Fi access points. I actually do this personally, as it's incredibly nice to have internet access through my regular internet connection instead of having to use cellular in such an event as a blackout. And this is because when everyone else loses power, and hence their internet, they all switch to using cellular from their phones, and the speeds become darn near unusable due to the amount of network congestion. And of course, another benefit to keeping the internet up when the power is out is that all of the services that I choose to self-host on my internet connection stay available for everyone that I share them with and who wants to use them. So my friends can still connect to and play on the Minecraft server even if the power's out at my house, because both the Minecraft server and the internet connection are on battery backup. However, for the network equipment part of this battery backup system, there is a bit of a stupidity to doing this the way that I am currently. Allow me to explain. The UPS uses batteries, which output DC, to power the devices connected to it in the event of a blackout. It does this by taking the DC voltage, usually around 12 or 24 volts DC, and passing it through an inverter to create 120 volts AC, which aligns with what usually comes out of the wall. But in the case of low power networking equipment, that 120 volts AC, in most cases, goes straight into a power brick that converts it back down to 12, 9, or 5 volts DC, depending on the exact equipment connected to it. Now, that conversion from DC to AC to DC is done surely because it makes compatibility easier, and it of course allows the UPS to work with other devices that don't use small external power bricks like a desktop computer. And I mean, can you imagine trying to explain to average consumers how to use different DC output jacks on the back of your UPS to connect low power gear, and also the sheer number of calls that you'd get from customers who plugged their 5-volt network switch into the 12-volt output and fried it? It would just turn into an overall nightmare for any company that would try to do this. And I say all of that to make it clear that I'm not calling the UPS manufacturers dumb or criticizing them for not doing what I'm about to attempt to today, because it makes sense for them not to. But for the people who are far deeper into this hobby than regular consumers, what if there was a DC-only UPS that takes AC in, converts it to DC to charge the batteries and power your devices, and then when the AC power drops out, it just uses the DC power from the batteries to power your devices through the already present DC to DC conversion circuitry. This would completely eliminate the power bricks and the unnecessary DC to AC and then back to DC conversion that come with using a regular UPS. And also, what if it was a modular design to suit many different configurations of appliances? For example, I have a 12-volt modem, 5-volt router, and 5-volt switch. So what if I installed a 12-volt module and two 5-volt modules into my DC UPS for my application? And then someone with a 12-volt and a 9-volt appliance could just use a single 12-volt and single 9-volt module, therefore allowing them to customize the device for their application. And that basically describes the device that I'm going to start work on in today's video. A modular, DC-only UPS that can be built by Homelabbers and anyone looking for a more efficient UPS option for their home networking gear that will get them more runtime. But before I get into developing and building the first prototype of this thing, I want to get something out of the way first, because I know this may be a deal breaker for some watchers. I know that my build videos almost always come with an instructable so that you can build my designs for yourself. But this video will not be paired with these open design instructions, as this project just isn't ready to be put out there yet. I haven't validated the safety of it, and it doesn't work quite as well as I intend it to just yet. But I'm putting this video out so that I can get community feedback on the designs and implement that in the next part of the development of this project. And with that out of the way, let's get into it. My design process started by creating the circuit that would handle the changeover between line power and battery power when the UPS detects that the power has gone out. This circuit was actually really easy to create using a basic relay, which when line power is present, has voltage across its coil that hence connects the main power bus to the line power supply. Then, when the line power supply drops out, the coil becomes unpowered and the normally closed contacts of the relay connect the downstream power modules to the 12-volt lead-acid battery pack. Now, there is some more nuance to this circuit, of course, that manifests in things such as the massive capacitor bank that helps the system survive changeover because the relay contacts are floating for a few milliseconds, but that one relay that handles the main changeover is really the most important part of this board. Now, on the same physical board as this circuit, I also included some other extra bits, which arguably are pretty important as well, such as a lead-acid battery charger circuit, an undervoltage cutoff switch for the batteries to prevent over-discharge, and a battery level indicator that's based around some super basic op-amps and voltage dividers, which really is only intended to give a rough idea of the battery charge, and that isn't very accurate at all. Apart from all of this, there's also some miscellaneous control circuitry on this board, and some power supplies for the power converter modules that will plug into this board. Speaking of those, I now started to think about how I wanted to do the power conversion modules that would allow different devices to be connected. I want to create several kinds of these modules. I'm thinking all of the main voltages like 5 volts, 9 volts, 12 volts, 15 volts, and 24 volts for any kind of barrel jack powered appliance. And then I also want to make some modules that work with USB-C PD and PPS for things such as Ubiquiti Unify equipment, whose lower power offerings use 5 volt, 5 amp USB-C PD power supplies for their power. But for today, I chose to keep it simple just to get a good proof of concept functional before complicating things with all kinds of different cards. So I began the design of a 12 volt, 3 amp card, and yes, I settled on a card-like form factor for these modules, where they'll plug into the main board almost exactly like PCI Express cards slot into a computer's motherboard. Now, I was torn on how to handle the voltage conversion on these cards after figuring out the form factor though, because the main power bus fed to these cards is unregulated. That meaning that when line power is present, it's a steady 12 volts. But when the power drops out, it becomes the raw battery voltage, which will obviously change by several volts as the batteries discharge. Now, as for being torn, I was mostly torn between using an inexpensive buck boost converter like this one, or one of the really nice Meanwell DC to DC converters that I used in my DIY SATA power distribution projects from several months ago. The reasons for going with a Meanwell module would be that it's unbelievably simple, I can trust it to be reliable, and it's got all of the necessary protections built in for me to trust it to be connected to an expensive piece of networking equipment. Now, the reason not to go with the Meanwell module would be that it's expensive. The reasons to go for the buck boost module would be that it's unbelievably cheap, its voltage is completely adjustable, meaning that you can buy a 5-pack of them and use 2 for a 12 volt card, 2 for a 5 volt card, and 1 for a 24 volt card with complete flexibility, and finally, it's probably good enough. Now, the reasons not to go with this kind of module are that I have no idea how good quality the power coming out of this will be. I don't think I can trust the onboard protections that it claims to have to work when I need them to, and these things have no datasheet, brand name, or other documentation that points to them being reliable for 24/7 use powering my expensive and sensitive networking equipment. And yet, a $30 DC to DC converter for each card you build is a little bit brutal. That's $120 for 4 cards. And I'm currently planning to design this device to work with 4 cards. So what I chose to do this time around was what I hoped would be a little bit more of a middle ground. I would use the cheaper buck boost converter, but I would build a whole bunch of protection circuitry around it. I would build my own overcurrent, undervoltage, and overvoltage protection circuitry on board of each card that constantly monitors the buck boost converter and ensures that it doesn't go rogue. And if it does, these protections should cut power, hopefully in time to save the networking equipment connected to it. And with this design figured out, the first breadboard prototype was born, and this prototype was of the card circuit, as I wanted to prototype the more complicated thing first. And this is what I ended up with. After, in the realm of 20 hours of tinkering and editing parts of the circuit to get it to work properly, which I of course didn't film because that would take up several terabytes of storage, I had a circuit that worked pretty well. Now, it's not completely flawless, as my reference voltage dividers aren't perfectly tuned to set the undervoltage, overvoltage, and overcurrent protection thresholds exactly where I want them, but once I have a PCB and the correct resistor values arrive in the mail, I can at least be confident that these circuits should trigger at the precise levels that I'll set them to. In terms of overall functionality though, this system trips when there's an undervoltage or overvoltage detected, and once I'm drawing much more than 3 amps on the output, the overcurrent protection steps in as well and will stop the power output. All of these protections can be reset by holding a button on the card for several seconds as well, so if one card in the UPS trips, it shouldn't affect the ability of any of the other cards to power their connected devices. So next, it was on to testing out the main switcher board that handles line to battery changeover. This first prototype didn't include any of the unnecessary parts, such as the LED level indicator and online versus on battery indicators, because I wanted to focus on the meat of the circuitry first, which meant that I started by testing just the battery charger circuit and the changeover circuit, which I hooked up to one of the buck boost converters that was powering a dummy load just to ensure that it wouldn't interact weirdly with the changeover. While monitoring the bus voltage with my oscilloscope when I pulled line power, I was able to see that even with a pretty solid load on the main bus, the changeover blip was relatively minimal. At this point, I had a load of roughly 3 amps on the main bus, and the main bus in this unit is only supposed to provide up to 8 amps at max to all cards combined. So yeah, this isn't a super high power UPS, but do remember that this is supposed to power a small modem, router, and a switch or two, which is all gear that you probably wouldn't want drawing much more than 50 watts in total anyways, as it's on 24/7 and that will drive your power bill up. So after seeing this pretty minimal blip with a nearly 50% load on the UPS, and knowing that in the final design there will be both more capacitance and less parasitic resistance to accentuate the voltage drop, as obviously I won't be building the final thing on breadboards, I figured that this was good enough. So after getting that part of the prototype done, I also worked to prototype the LED indicator circuits after this, just so that I could cover all of my bases. But there's not too much to mention in this regard, so let's move on to the next major step, designing and ordering the PCBs. I designed 2 separate PCBs for this project, one for the main board and one for the 12-volt 3-amp card. And after designing both boards, I went over to the website of today's video sponsor, PCBWay, and placed orders for these PCBs. PCBWay is a company that offers high-quality custom manufacturing services, including things such as PCB manufacturing and assembly, CNC machining, sheet metal production, and 3D printing. I've used their services many times, and the ordering process has always been simple, and the resulting products have never failed to make my project feel more polished and professional. Plus, if you've got any projects in the works, you have to check out their 12th anniversary sale, which is going on right now. You can participate in some fun mini games, earn some coupons, and take advantage of some other sales that they're running. Namely, special colors like purple, matte black, and pink that would usually cost more are now discounted to the same price as the standard colors. Plus, you can also get up to 50% off of their 3D printing service. So if you like to build things like me, I strongly recommend that you check out what PCBWay has to offer at the link in the video description, and don't miss out on their anniversary sale. A couple weeks later, my 2 PCBs for this project had arrived, the green one being for the main board and the red one being for the 12-volt card. I assembled the main board first, as the card doesn't really work without it, and I don't have many notes on the assembly of this thing. I designed it to be pretty easy to build and work on, and I used all through-hole components as I find those easier to troubleshoot with, because you can easily snip a leg to test how disconnecting something changes the circuit's behavior. And once you're done with that test, you can repair the connection by just adding a small blob of solder to it. Plus, I also find that adding bodge wires is much easier with this kind of circuitry as well. And considering that this is my board for V1, which is almost certain to have some quirks that will need to be worked out, I think doing this was a wise choice. And the exact same thing goes for the design and assembly of the 12-volt 3-amp card. Now, you might notice that the circuitry on this thing is really complicated, and yeah, it kinda is. It's also probably way overcomplicated, as this happened because I thought it would be fun to challenge myself to do all of the protection circuitry completely analog, with no microcontrollers involved whatsoever. Now, this was a ton of fun to design and prototype, but it did result in a very large circuit that will probably be replaced with a microcontroller like the Pi Pico or Arduino Nano in future versions of this project. Plus, ironically, the cost of all the components used in the protection circuit likely adds up to around the $25 to $30 that one of those Meanwell modules costs. But hey, it's a V1, we're starting somewhere. After the boards were assembled, I took the main board and plugged it into my lab bench power supply with a pretty conservative current limit set to make sure that it wouldn't explode, and that I was receiving the correct voltages on the correct pins for the cards. Thankfully, the board didn't light on fire immediately and actually seemed to work almost just fine. However, one of the 5-volt rails was missing on all of the card connectors, and after doing some investigation, it seems that an LM317 jumped the wall in my component organizer tray and made it into the L7805 bin, where I accidentally grabbed it and soldered it in a place where there should have been an L7805. After replacing this regulator, everything checked out as I expected it to, and I moved on to plugging in the card to one of the slots. The card also didn't blow up once installed and seemed to work mostly fine as well, other than the fact that it was constantly throwing an alarm. I tracked this down to being a bad 2N3906 transistor on the board, and after replacing that, I was able to reset the alarm and have it actually stick. There are some quirks with this still, namely that the unit will always throw an alarm when power is first applied, but I'll do some more investigation into that in the future, as it's not too huge of a deal. But alright, the initial anti-explosion tests are done, and now I'm going to take a break and get the heatsink for the main PCB prepared, as the two LM317Ts that make up the battery charger circuit and the large MBR1060G diode that lives across the main power bus will get far too hot if not cooled, and I need to do some tests where I'm going to be using these components pretty intensely. So I used this heatsink to cool them, which after painstakingly cleaning the thermal adhesive off of, I trimmed to size with a hacksaw and drilled and tapped 3 M3 holes in so that I could mount all 3 TO220 package components to it. And with that, it's time for a pretty large step in this project, connecting the lead acid battery. Now, this is a big step because the lead acid battery, while not the size of a car battery or anything, can still dump way more current into any problematic circuitry than my lab bench power supply ever could. So if I've messed up, I'll know because it will blow up violently. Though I hope that it wouldn't go too crazy, as I do have common sense and have the battery connected through fuses to the rest of the circuit, but anything could technically happen. To my relief, when I connected the battery to the circuit through an ammeter, I saw a whopping 0 milliamps of current flow, which is exactly what I want to see. I was also able to see that the battery charger circuit does its job of charging the battery with 600 milliamps of constant current perfectly as well, just as it did on the breadboard. And this made me quite happy, though the LED battery level indicator was absolutely not doing its job correctly. But it is a bit of a poor design for this function from the start, and is honestly completely unnecessary for the functionality of this board, so I'm going to be fully ignoring that issue for now. On a better note, when I pulled the power from the bench power supply, which represents line power by the way, the board switched over to battery power perfectly, as is indicated by the roughly 350 milliamp draw from the battery and the on battery LED illuminating. Wonderful. Everything seems to be generally in working order, minus a couple of non-deal breaking issues that frankly can be dealt with later, assuming I've got the rest of the system functional, which I do still need to test a bit. This is because while I've of course managed to successfully switch to battery under no load, I have not tested this circuitry under load. And so I connected a dummy load to the 12-volt card to draw a little more than 2 amps from its output. And this is where the first major issue arose. When I pulled line power, the system seemed to successfully switch over to battery power for the first 1 second, but then it shut down, meaning the battery cutoff was being triggered, as this will shut down battery power and lock the system out of drawing from the battery until line power is restored. Interestingly though, when having the load on the card to draw a little more than 1 amp instead of 2 amps, the changeover almost worked. This time, instead of failing to stay powered on, the mainboard switched to battery power and it stayed on perfectly, but the card threw an alarm and shut down every time, meaning the UPS is pretty useless. I'll have to address that alarm issue on the card in a minute, but to tackle the changeover failing under high load, I figured that the issue was the op-amp circuit that checks if the battery voltage is too low, and if it is, triggers the cutoff circuit. The mistake with this part of the circuit was that I accidentally wired it to probe the VCC bus, which is the main power bus for the cards, and not the VBAT bus, which is just the battery's positive power connection. This means that when a changeover at high power happens, the higher current flow depletes the capacitor bank to a more extreme degree and causes a larger voltage drop to take place across the power Schottky diode once battery power is present, meaning that the voltage the measurement circuit sees is momentarily way lower than the battery voltage ever gets, and also also way lower than the threshold for the over discharge protection to trip, meaning that it does trip immediately after a changeover occurs. Even 2 batteries in parallel for better current handling and less voltage sag doesn't fix the issue, because the probe is measuring at the wrong spot. I was able to verify this theory by temporarily cutting pin 1 of the LM358 op-amp, which disabled it from ever being able to trip the cutoff circuit. After doing this, the changeover was perfectly reliable even at high load. Alright, time to tackle that protection alarm tripping on the card now. After, of course, setting the project down for a little while so that I could come back to it with a fresh mind, as at this point I was running out of ideas and was starting to feel a little bit of burnout. But once I came back to it and got to troubleshooting, I figured that first off, I was very certain that it was something to do with the buck boost modules not being able to keep their output voltage in check when the changeover occurred, hence causing either the over or under voltage protections on the card to trip. I was cued into this by the fact that the input power to the module was being cut alongside the output power from it when the alarm was thrown, and this is behavior that only happens when either the over or under voltage protections are triggered, as overcurrent protection only cuts the output of the module. And these protections are working well and are pretty strict. Over voltage trips at just above 12.1 volts and under voltage trips just under 11.7. So I grabbed my oscilloscope to watch the output of the module when the changeover happened, to see if I could see a small dip or peak before the main cutoff occurred, but I was only able to see the main cutoff on the output. However, when I took the scope probe and brought it closer and closer to the output of the buck boost converter before the couple of capacitors that are on the card to smooth the output even more, I noticed that holy cow, these things output absolute garbage quality DC. There are little peaks and dips all over the place, resulting in multiple volts worth of ripple. These all were mostly smoothed by the output because on my PCB, there are some capacitors across the output of the converter, but right at the output of the module, where the probe for the over and under voltage is, the power is junk. So it's very possible that when the module is stressed more during the changeover, the noise gets worse momentarily and it becomes just enough to tip the protections over the edge. Another aspect of this that I found interesting was that the output capacitors on the module got very hot under load, and they seem to be the source of their own heat, meaning that they aren't just hot because something close to them is also hot. This is a sign that these capacitors may be really low quality and high ESR ones, and possibly recapping the DC to DC converter could fix this issue. So I removed the module and desoldered the 2 output capacitors so that I could test them. And yes, I know that these say they're Sanyo capacitors, which is a good manufacturer, but with how cheap these modules are, I'm 99.9% certain that these are fake Sanyo caps. Curiously enough though, these capacitors measured fine when I tested them. Both the 470 microfarad and 220 microfarad capacitor came back with very on-point capacitances and low ESR ratings. So that's quite odd. But I chose to trust my gut feeling that these capacitors might still suck, and I replaced the 470 microfarad one with a nice Kemet branded one that I'm sure is real because I bought it from a reputable dealer. The Kemet one did technically test with a much lower ESR too, so I figured it had to be worth a shot. I left the 220 microfarad capacitor original because I didn't have a good replacement on hand. After rebuilding the module and connecting it to the card with its new main output capacitor, I went back to testing, and I still find it somewhat hard to believe myself, but this actually fixed the issue. Somehow, this legitimately fixed the alarm tripping during changeover issue completely, and even with the card near maximum load, drawing about 2.7 amps from the output, with 100% consistency across several tests, the changeover happened successfully. I did choose to take a look at the power coming out of the module again on the scope, but it was still kinda crap. But I guess now it was not so crap that the card was unhappy with it. I think more work needs to be done here, but I at least know what track I need to be on for future versions of these converters. Alright, so the card tripping at changeover issue is resolved, and the changeover shutdown issue is mostly figured out as well, the issue being the undervoltage sensing circuitry. However, instead of leaving my only form of over discharge protection disconnected, as it is right now, I think I should add a small bodge wire to reconnect its sense probe from VCC to VBAT, which is where it's supposed to be. I did this, and after doing so and reconnecting the op-amp's output pin, the changeover still worked under high load, and I had functional over-discharge protection as well, which is what I intended from the start. And so, with a mostly functional prototype, or at least a prototype that's got all of its basic functions in check, it's time to run one real-world test before I end this video so I can hear your feedback for the next revision of this project. This is an old Netgear Wi-Fi access point that I've got laying around, and I'll use this as my demo because it's not a mission-critical piece of infrastructure for me currently. Fun fact, I'd really rather not fry my actual router while prototyping this thing, because then I'll have a problematic circuit and no internet to troubleshoot it with. Conveniently, this access point, while supporting PoE, also supports a 12-volt barrel jack input, which I'll use right now. After plugging the access point in and powering it with the UPS online power, I ran into several issues with the card's alarm triggering during the boot up process of the AP, and sometimes it was getting really close to triggering, but not quite doing so, which was quite odd. I think the issue here is that these buck boost modules really just have awful voltage regulation, and the access point, unlike my resistive dummy load that didn't changes how much current it draws pretty constantly and pretty abruptly, causing the voltage protections to trip as the module struggles to hold a constant output voltage under varying load. My temporary solution to this was a 2200 microfarad capacitor across the output of the card. This allowed the access point to fully boot up and bring its two radios online. And after seeing this, I connected the AP to a non-PoE switch so that it's still fully powered by the UPS, and then I connected my phone to the network that it was broadcasting. Once I was connected, I ran a speed test, and I thought this was interesting and also a really good way to know that I'm not faking my connection to this AP, but you can actually see the power draw go up on the power supply when I start the test as the AP has to work harder to pass more traffic. So knowing the AP is powered just fine off of the UPS online power and that it can pass plenty of traffic, it's time for the real test, pulling the plug on line power while mid-speed test. So I started the speed test and then pulled the line power from the UPS, and without a hitch, the AP got powered off of the battery backup and my speed test kept running. So with that, I think that I can say that V1 of this project looks very promising, as I've technically just successfully prevented a power outage from taking a network offline. Now, I still need to narrow down my approach to what DC to DC conversion I will use in future versions of this project, as the stuff that I'm using currently clearly has many issues, and I don't really like the fact that it feels like I'm just band-aiding over all of them, resulting in a card that really just shouldn't exist. I would also like to figure out a good way to get rid of the big Schottky diode that all of the main bus current passes through for the sake of efficiency. Finally, I also need to fix the level meter, and assuming I continue to build my own protection circuits, I need to fix the alarms that get thrown right after the boot up on the cards. And if you can think of anything else that could be improved on this project, or features that need to be added, drop it in the comments below. I'll have the full schematics for the card and the mainboard on screen at the end of the video so that you can screenshot and inspect them, and tell me what might make sense to change. At the time of this video going live, I have not started work on V2, and therefore, I should easily be able to implement any ideas that you guys provide that align with the goal of the project without having that barrier of having to rebuild my partially done V2 designs to do so. Basically, it's an open house. Go wild, and hopefully together we can make V2 way better than V1. Well, that's all that I have for you in this video. I hope that you were able to at least enjoy it and maybe even learn a thing or two. In any case, I hope to see you next time. Goodbye.